Okay, let's resume. So in the last class we started to look at the poles and zeros in the common source. So let me recap that and we'll continue from that. So the common source I considered initially was this. I took a small signal Vin and assumed that I had a source resistance for this case. So common source, so I have the input fed to the gate of the transistor, and I assume that I have a PMOS current source here. So this is small signal ground and this is my output, and here I lumped all the capacitors from the gate to the ground as a capacitor C1 and the capacitors from the output to the ground I lumped into one single capacitor C2, and I basically finally replace this with an OTA symbol. So actually let me do that here so that it's clear. So I am trying to basically replace this transistor with the symbol of OTA, because you know for small signals this is a voltage controlled current source. So what I'll have is the following. Let me remove this. I'll have the OTA here. This is the output, right? So one thing should be clear: for the current flows from which terminal to which terminal in a MOSFET? Drain to source. So this should be what terminal? Or this is the output terminal. Output terminal is drain or source in the MOSFET. So this should be the drain. So how do you figure out if this is the gate or this is the source? Okay, you're saying source is grounded. Yeah, okay. Okay, maybe the other way to say is, how do you determine if, let us say, this is the plus terminal or minus terminal? Yeah, the question is that, right? Sorry, plus. So this should be at the gate. Oops, sorry, hold on. Why is this happening here? This is the gate, is it? Sure. Why? I mean, how do you figure out if it's correct or wrong? Okay, let's try that. Let's say increase the voltage here. The current is flowing from the left to right or right to left? I mean, left to right or right left, because you are laterally inverted to me. I mean, I'm increasing the potential. I mean, I'm increasing the voltage on the positive terminal or negative terminal. If positive terminal voltage increases, the current will be pushed out or pulled in. So current should flow from left to right or right to left? Left to right. Okay. So here if I increase the gate voltage, the current is flowing this way or this way. That is, it is flowing, let's say this is called, this I'll call it as option 1, this I'll call it as option 2. Option? If I increase the gate voltage, the current flow is as marked in direction 1 or direction 2? Current flows from which terminal to which terminal? So drain to source. In MOS, so what is the correct thing? 1 or 2? So this is how it flows. So now tell me if this should be gate or source. I mean, here the current is flowing this way, but I see that the current is basically flowing in the reverse direction here. So which means this should be the, this is basically the source terminal, this is the gate terminal. Fine. I mean, source is basically grounded, that much everyone was comfortable with. My question was whether the source is the positive or the negative terminal. Is it clear that this should be the gate should be the negative terminal? Okay, fine. So if that is clear, I'll erase this. So this has, what is the short circuit GM of this fellow? By M1, M2, what is the short circuit GM here? GM of which transistor contributes to short circuit GM? So this I'll say it as a short circuit GM of GM1, and I have an intrinsic output resistance. I'll call it some R0. So what is the intrinsic output resistance here? The output resistance is what here? Looking down, I'm looking into the drain of the transistor M1, R0 of. Looking up, what is it? So that's how I macro model this fellow. And of course at the output I have already lumped the capacitor C2. Okay. So I'll basically erase the right side portion. Hopefully this is clear. Is that okay? So, or maybe let it be there for a minute. It's here. I basically ignored the capacitor from gate to drain. That is, the capacitor from here to here I've ignored. So if I ignore that capacitor, can you tell me the location of the poles here in this circuit? There is no R1 here. Yeah, I mean you have two RC sections. Are they coupled or uncoupled? Uncoupled, because this fellow is kind of providing a high input impedance and isolating the two. So this RC section gives rise to a pole 1 by Rs times C1. I'll write it as conductance Gs by C1. Similarly, what can you say about the pole contributed by this RC section? Yeah, 1 by R0 times C2. I'll call it as the output conductance G0 by C2. Same. So this was simple. So next I consider the case where I include the effect of the capacitor across the OTA. So this is R0, this is GM1. So here I have a lumped capacitor and I call that as C1. Here I call it as C2, and here I include the capacitor from gate to drain. Typically, as I mentioned, gate to drain capacitance, the value of the capacitance is much smaller, but for hypothetical case, we'll assume that I'm going and putting an explicit capacitor across gate and drain so that this becomes a dominant cap. That is, the capacitor is not so negligible. So here, as we saw, the capacitors are not coupled, they are strongly coupled because of addition of this cap. So we had to basically compute the transfer function and find the roots of the polynomial, and I approximated the polynomial. Where did I approximate? Let me just copy the expressions. Yeah, these were the roots of the quadratic equation. Again, sorry, I didn't solve the roots of this. Instead, we assume that the poles are far apart, and assume that if the roots are far apart for a quadratic polynomial, we can approximate the roots as ratio of the polynomial coefficients. So that gave rise to these. So let me just copy it here. So then we decided to see if we can understand why the location of these poles makes sense, and that's where we came across this effect. That is, if I take a voltage amplifier, when I draw it as a voltage amplifier, I am referring to what kind of a control source? Voltage controlled VCVS. So in that case, I saw that if I have an impedance, let us say it's a capacitor, for example, connected across the voltage amplifier, and if I attempt to find the looking in impedance, as usual I'll apply a test voltage Vt of S, which means what will be the voltage at this node? Minus A times Vt of S. Then what can you say about the current drawn here? This voltage is Vt, this is minus A Vt. So this is 1 plus A times, or I'll write it the other way, I'll write it as Vt of S times 1 plus A times C times S. So which means the looking in impedance is a capacitance. What is the value of the capacitance? And this is what is referred to as Miller effect. Again, we saw it in the last class, I am quickly recapping. So which means I can do the following. Whenever I have a floating impedance like this, by floating impedance I mean both the terminals of that impedance is connected to some non-zero nodes. If I have a floating impedance connected across a voltage amplifier, I can basically reflect that impedance as a grounded impedance at the input side, and the value of the capacitance here is how much? 1 plus A times C. Now similarly, we can also argue the other way, that is, if I have minus a here, again the same thing. I can argue that, let us say, if this voltage is Vx, this will be minus Vx by A. So which means the current drawn in this branch is going to be Vx into 1 plus 1 by A times Sc. So to model the current drawn in this branch, you can say that I have a capacitor here with a value C into 1 plus 1 by A. Again, as I mentioned, being a voltage controlled voltage source, this result is not really useful, because I can replace this capacitor with an elephant, nothing changes in the world. The VCVS will make sure the voltage is the same irrespective of what you put here. But what will be useful is this fact that the input side resistance or input side impedance is a capacitance with a large value, right? Now this is nice, but this Miller effect, as we discussed, is in the context of what kind of control source? Voltage control voltage source. That is important, because if I had to use the Miller effect, I need to know the exact voltage gain from that input node to the output node, and if it's a VCVS, that voltage gain from this node to this node, what is the voltage gain? Yeah, it is a constant which is minus A. Across frequencies it is constant, it's a single value minus A, right? But fortunately or unfortunately, we are not dealing with a voltage control voltage source here. What kind of control source we are looking at? Voltage control current source. Again, we are looking at the pole location, so I can discard the input. Okay. So this is a voltage controlled current source. So which means if I were to use this result we saw, I need to be exactly finding the voltage gain from the input to the output node, which means here I need to know the exact voltage gain from this node. I will make some space, hold on. So okay, I will use this here. This is C1. Okay. And I have this. Okay. So if I were to use the Miller effect here, I need to compute the exact voltage gain from this node to this node. But being a voltage controlled current source, in this case, at the output side, what quantity is fixed here? The current is fixed. So which means if I ask the transfer function from this voltage to this current, what will be the ratio of this current to this voltage? Sorry? GM or something else? Can you look carefully? I mean, maybe if it's not clear, I'm looking at the current flowing this way. I'm interested in the, I mean, if I know this voltage, what does this current? GM times or minus GM times? Minus GM times. So which means if I'm interested in the transfer function from this voltage to this current, that is a constant number equal to minus GM. Whereas unfortunately, I'm interested to find the relation from this node voltage to that voltage. And this voltage will depend on this current and whatever impedance is connected at the node. And that is a combination of these fellows and this capacitor. So the gain will no longer be a single number minus A as we saw in the VCVS case. Here it was a single number, but here it will actually depend on the frequency. So you will get a frequency dependent gain. So which means if you were to use Miller effect, you have to take into account this frequency dependent gain and do it. And that's actually much more complicated than a normal transfer function calculation. But as I mentioned, that's where we engineers, we always come up with some workarounds. And the workaround we do for this is the following. If let us say I look at low frequencies. For low frequencies, what can you say about the capacitors? Capacitors can be treated as open circuit. So if I were to draw only the VCVS portion, so I'll have something like this. All the capacitors, the blue ones, are open circuited. I have only the intrinsic output resistance R naught. Then what can you say about the voltage gain from this node to this node? What is this current? If this voltage is some Vx, this current will be how much? Minus Gm times Vx. So what will be this voltage? Yeah, so the gain is going to be minus Gm1 times. So which means now this gain is no longer a function of frequency. I can say that the gain is approximately a constant equal to minus, or I mean, I'll not confuse, I'll say the magnitude of the gain is basically. So which means now I can approximately use the Miller effect, which is what we refer to as Miller approximation, right? Which means now I know the gain from this node to this node is approximately minus Gm R naught, which means if I have a capacitor connected between these two nodes, I can reflect it as a single capacitor at the input. What will be the capacitance value at the input then? C into 1 plus A. What is the value of A here? Gm R naught. So which means I can redraw the circuit now like this. So this is Rs. So I already have C1. In addition to this, I'll have a capacitor whose value is C into 1 plus Gm1 R naught. And then I have the OTA like this. Okay. So which means now you see earlier this capacitor was strongly coupling the input and the output nodes. Now the coupling is completely gone. So you can treat it as an isolated RC section. So what will be the pole associated with that RC section? Yeah, what is we'll write as conductance by capacitance. The conductance is how much? By capacitance is C1 plus C into 1 plus Gm1 R. Again, remember we are making an assumption that we are dealing with low frequencies, which means the pole we compute is a low frequency pole or high frequency pole. If this pole is indeed a low frequency pole, our assumption is fine. Okay, but that is something we already kind of verified when we solved the quadratic equation. So when we solved and got the expression for this pole, we already convinced that this is a smaller frequency pole. So it is okay. And if I compare the result I got by solving the quadratic equation approximately and what we got from our intuition, oops, okay. So these are the two terms. So as you see in the numerator, I am completely fine. I have GS. Denominator, I have this C1 plus C into 1 plus Gm R naught. I have the additional error term, which we saw that it is okay because this itself is an approximation, and the roots of the quadratic equation itself was an approximation. So a lot of things might give rise to this, but in practice, this term will be the dominant factor because I have a capacitor times a gain. So this will be the most dominant factor. Is that clear? So this is where we stopped in the last class, and now at least we know why the low frequency pole location makes sense. By looking at the circuit, we should be able to write the pole location. Is that okay? So we understood the location for the low frequency pole. So what next? Yeah, should not leave high frequencies. So let's look at high frequency pole. And this is where a common confusion arises among the students. So we already saw that with Miller effect, this capacitor here I can reflect at the input side with a value C into 1 plus A. At the output side I can reflect it with a value C into 1 plus 1 by A. So the question that usually comes is the following. Let me copy this. Let me erase this. This is not relevant now. So why don't I basically reflect this capacitor here at the output side and say that the value of the capacitor is C into 1 plus 1 by Gm1 R naught, and then in addition to this I'll have the C2 here and the R naught here, and then say that the pole is this conductance by this capacitance. Can I do that or can I not do that? We cannot. Why can't we do that? Where I'm not able to see. I'm able to. This is.
Because this is high frequency.
So.
And in high frequency, you are considering that capacitor is open.
So what he is pointing out is the following. Remember, we actually did not use the Miller effect completely, but instead, what did we do here? We did a low frequency approximation that this gain minus A of S can be approximated as a constant GMR0. So this is not a gain for all frequencies. This is a gain for what frequencies? Low frequencies. Only for low frequencies, as he pointed out, I can assume that capacitors are open. So the gain from this to this is minus GMR0. So to simply put, I cannot use this low frequency gain and compute a high frequency pole. Yeah.
We don't know that the high frequency pole yet.
Yeah, we don't know it. But what I'm saying is, we already know that this is a low frequency pole.
Yes.
Correct? Now, I cannot say that the second pole, I can compute it this way, and I cannot call that as a high frequency pole. Your question is, do we already know if it's high frequency pole or not?
No.
We don't know. Yeah, but
So that we can do right now.
oh, you can do right now. But the point is, then you are assuming both the poles are basically low frequency poles. Correct? So which means even to start off, we already know some results, right? See, we are not doing a blind calculation. We already had some understanding that when I had to solve for this, I had to make this assumption. See, I had a quadratic polynomial. I already first solved for this. And to solve for this, I had to make an assumption that the roots are far apart. So which means if one was at a low frequency, other should naturally be at high frequency. Correct?
So, but we did while solving exactly this.
Uh,
This equation we got
Mhm.
by doing exact calculation.
Correct.
And now we are doing approximation.
No, we are not approximation. We are trying to see how we can get it by inspection.
Okay.
Correct? It is an approximation in the sense that we know this is a low frequency pole. So at low frequencies, we can do some things and get this low frequency behavior here. Right? But I cannot use the same effect. I cannot use the same gain here and try to compute a pole and call that as a high frequency pole. Right? Because I already know that one of the poles at a high frequency. So in fact, if instead of this, if you go and use the high frequency gain A of S, it might work. But that's a convolved approach. So instead, the high frequency pole can be understood in a slightly easier way. See, one thing is for sure, right? Earlier when I didn't have the capacitor C, the two nodes were uncoupled. So I could directly look at the capacitance at this node, conductance at this node, I was fine. So now the issue is because this capacitor is coupling it. But somehow at low frequencies I decoupled it, and I could say the low frequency pole is this conductance by this capacitance. Similarly, let's try to see at high frequencies we can do something and try to write the pole as the conductance and capacitance at this node. Okay, but we cannot say this is the capacitance at the output. Let's see what happens. So let me actually copy paste this. So now tell me, I am dealing with high frequencies. At high frequencies, I have the resistor and capacitor here at the input side. Among these two, which will offer a low impedance? RS or C1? So if I have these two impedances in parallel, what can I approximate them as? C1, because this is going to offer a lower impedance. So essentially I can ignore this. So which means I can try to find the effective conductance and capacitance at the output side and then try to see if that makes sense. So essentially I'm interested to find the output impedance here. So how will I find the impedance looking into the output end? What will I do? I apply? Yeah, same thing. Vt of S here. T of S. And I mean, one thing is for sure. What can you say about R0 and C2? Yeah, I mean these two will appear. I mean in your final output impedance, these two are going to come in parallel. So I know that these two are already in parallel. So I can I'll say it is here already. So I'll compute the impedance here. Then I can say that whatever I compute is in parallel with this. So I don't have to worry about this for now. Okay. I'll isolate that and find the rest of the impedance, and whatever I compute here is in parallel with it. That's the idea. So now this voltage is V test. So this is the current I test. So this current I test can flow in how many directions from here? What are the paths? One path is through what? Yeah, one path is through this capacitor. Other path is? Yeah. Yeah. The idea is, see, now we are trying to look at the pole, right? So the idea is you find the conductance at that pole and the capacitance at that node. Sorry, conductance at that node and the capacitance at that node. That's what you are trying to find. So if you ignore the conductance, then you don't get anything. Yeah. Because the idea is now at this side I know I have a low frequency pole. So which means for this side I can make the approximation that C1 will dominate compared to others. Okay. Yeah, so coming to the current, this current can flow here. What is the other path? Through this fellow. So what can you say about the current flowing here? Can you give me the expression for this current? I mean, what is the current flowing here? So basically these two capacitors are in what kind of connection? Series. So the current will be how much? Pt of S times S times C times C1 by. That's basically the two capacitors in series. Now if I were to find this current, what should I find first? I mean, what is, fixing this current? Voltage where? At this node. So what is this voltage? V test. Then what can you say about this voltage? I mean, again, is there any current flowing here? So I apply this. I know this voltage here. I'm interested to find this voltage. How will you find it? Voltage division. What is the voltage division? That's what I ask. I mean, yeah, it is Vt of S times what is the ratio? C1. I mean, is it C1 by C plus C1 or C by C plus C1? I'm hoping this much is clear. So what is the current in this direction then? It will be minus or plus. I am looking at the current flowing this way. I know this voltage. What is the current flowing this way? Minus or plus? Plus. So GM1 times C by C plus C1 times Pt of S. So what is my total test current? It's basically Vt of S times S times equivalent capacitance times Vt of S times GM1 C by C plus C1. So this is an effective capacitance, and what is this? I mean, the current here is real or imaginary? The current here is imaginary or real? Or the other way to say is, I mean, if you have to model this behavior, how will you model it? Using circuit elements. I have Vt of S. Using simple circuit elements, how can I model this current? I mean, what is the current dependent on? I mean, can you tell me in English the current and the voltage? How is it? How are they related? Huh? The current and voltage are linearly related. How would you model that? I mean, 8th standard students will tell this. Tell me. Resistor. What is the value of the resistor? Is it GM or 1 by GM? Come on, you cannot make this mistake again. Correct. So this will model this part. How do you model this part? I'll show this. Yeah. What should I add here? This is my test current. Test current has two parts. This part is taken care of this, and I should take care of this part of the current. How will I do that? What should I add in parallel? What is the value of the capacitor? Yeah, C equivalent. And what is the equivalent capacitance? C1 by. So that is basically the looking in resistance here. So as you see, interestingly, this becomes a first order RC section at the output end, correct? But my total output impedance is not just this. What should I include along with this? I'll basically add C2 to this, and to the resistor what should happen? Yeah, parallel to R0, I will say the conductance is getting added here. Okay. Again, this can be, you can look at this by inspection and make sense also. So at least now we know that at the output we have a first order RC section, right? So you find the total capacitance here. The capacitance is C2 in parallel to series combination of C and C1. That's what you get, C2 in parallel to series combination of C and C1. Now if you look at the resistance or the conductance, I have R0, that is the G0, and remember that here I have a GM input in feedback, right? See, if I have a case like this, what is the resistance looking here? Remember that this is going to be a transistor finally. For a transistor, I am basically doing this, correct? Whereas here, I am not feeding the exact signal here, only a fraction of this signal is fed back here. So that fraction is basically that capacitive division, which is Gm times C by C plus C. So now we can try to write the pole location. This is a first order system. So what is the pole location? I mean, I have R and C. What is the pole location? Yeah, let's write as conductance. What is the conductance of this fellow? It is Gm1 times C by C plus C1 plus G0 by capacitance is this is going to be my high frequency pole. Again, you can look at it and write it. I am trying to write the capacitance. So I have C2 here, that is in parallel with series combination of C and C1. That's why the denominator makes sense. Now if I were to write the conductance, I obviously have the conductance R0 or the G0 term, but I also have a real conductance because this GM block is put in feedback. Again, remember, if I have a connection like this, that is 1 by Gm, but here I don't feed the entire signal back to the inverting terminal. Only a fraction of the signal is fed back at the inverting terminal. So we have Gm times the capacitive division, which is C by C plus C. Okay. So this is what we get from our attempt at understanding the location of the pole. Let's look at what is the actual pole location we got from the approximate solution. So this is what I got. So let's can quickly compare. I have the denominator is fine. I mean, this is basically, sorry, this should have been C2. Okay. Yeah. So denominator is same. Numerator I have this part G0 and then Gm1 times C by C plus C1. Of course, I have an extra term here. Again, you can attribute to all the approximations we did. But in practice, remember, my Gm times R0 is going to be much greater than 1. So which means Gm is going to be much greater than G0. So in the numerator, among the two terms which I have here, among these two terms I have in the numerator, which will dominate? So I can basically approximate as this term by this. So that's why this approximation we write for the pole location is good enough in practice. Yeah.
After we just doing that on the approximation. So how we just check like whether which pole is the low frequency pole, whether the input side or output side?
Okay, good question. At least you know from Miller effect that if I have an ideal VCVS, the capacitance looking here is going to be really large. So at the input end, I will have a large capacitor. So whatever pole you compute at the input node, will that be a low frequency pole or high frequency pole? So at least that should be clear that if I use the Miller effect, the pole I get here should be at a much lower frequency, which means naturally the other pole should be at a higher frequency. So maybe let me summarize this. So now let's try to write the pole locations directly based on the understanding we have. Let's try to write the low frequency pole, right? For writing the low frequency pole, we make the Miller approximation, wherein we assume that the gain from this input node to this output node is how much? What did we assume the low frequency gain from this node to this node as? Minus or plus? Minus GM1 times. Okay. So which means now can you help me write the low frequency pole directly? It is going to be the conductance at this node by the capacitance at this node. What is the conductance at this node? I only have RS, so that will result in a conductance of GS. By I have to write the total capacitance at this node. What are the capacitors I have here? I obviously have C1, no brainer. Plus this capacitor will get multiplied by the gain, the low frequency gain, C into 1 plus. So this we should be able to write by looking at it now. We don't have to. Oops, sorry. Yeah, that's the gain, right? Low frequency gain from this node to this node. I mean, remember we looked at the low frequency gain from this node to this node is minus J1 or not. That's what I have written. Similarly, let's try to write the high frequency pole. For that, I try to do a similar exercise. I try to find the total capacitance at the output node and the total conductance at the output node. What is the capacitance here? I definitely have C2. This will come in parallel with these two fellows connected in series. Is that clear? So the location will be, what will be the capacitance now? C2 is in parallel with series combination of C and C1. That is C1 by. That is the capacitance. Similarly, what can you say about the conductance here? I have, what is the conductance at this node? I definitely have this R0. That will result in a conductance of G0. Plus I have something in parallel. And who is contributing to the additional conductance here? GM1. Because as we saw, if I put it in feedback, the resistance is basically 1 by GM. But now it is not completely put in feedback. We have a fraction of the GM. So what is the fraction of GM? So I need to find what fraction of this voltage appears here. That is a capacitive division between these two fellows. C by. Is that clear? So that's how we can look at it and try to write it. You don't have to really memorize it. Once you understand the fact that we use Miller approximation for low frequencies, you can write the low frequency pole here. Similarly, at high frequencies, we ignore RS, then look at the total conductance and capacitance at the output node. Capacitance is this and these two in parallel. The conductance might not be very trivial because you have R0, but you also have this GM put in feedback, giving rise to a resistive or conductive component. Is that clear? Yeah. Low frequency pole. Okay. So I already know that I'm trying to find a low frequency pole. So which means I approximate the gain. See, everything starts from the Miller effect. What point do you have? Okay. See, I know that I'm going to use Miller approximation and break the coupling here by reflecting this capacitance as an equivalent capacitance at the input side. That's all. And the value of that capacitance will be this C times 1 plus the low frequency gain. That is C times 1 plus the low frequency gain, which is 1 plus J1 normal. So again, you don't have to really memorize it. If you understand this, you should be able to write it. Great. So yeah, one other thing. So here, when I didn't consider the coupling capacitor here, these were the pole locations. Now let me assume that all the capacitances are all of similar order or similar value. Similarly, the GS and G0 are of similar order. Then what can you tell about these two pole locations? Do you think they are close by or they are far apart? They might be really close by. But the moment I added this capacitor to couple those two nodes, what can you say about these two pole locations? They are close or far apart? They basically are far apart. So this effect is often referred to as pole splitting. This is something we might come back to few classes down the line. So good to have in mind. Any questions so far?